Hey guys, so in this one we are going to go through the short answer questions or short/extended answer questions of the revision test. All right, so the first one, determine the minimum spanning tree. So a very sort of straightforward application of Prim's algorithm. All right, so usually when doing this in a test, SAC question, whatever, just highlight over the existing one. So we got 7 is the smallest edge, 8 is the next is 9. The smallest value edge to get to here is 10, and the smallest to get to there is 12. So the total, or the sum of all those edges, is 46. All right, consider the network diagram shown. A forward scan has been started. Complete the scan, then determine the earliest completion time. So 1 mark for completing the scan, 1 mark for determining the earliest completion. All right, it's up here will be 15, it'll be the 8 and then the 7. There are a lot of vertices in here, so just be very careful. This would be 11. This would be 16, the 11 plus the 5. Up here would be 25, 15, and 10. Down here would have to be 19. Here would have to be 32, which is on 40. So that's the completed forward scan. The earliest completion time is 40. This question doesn't have any context to it. We don't know if it's minutes, weeks, hours, whatever. So we'll just leave it as 40. All right. 7 work sites are set up for the reopening program for the reservoir and are placed nearby the reservoir in the 5 town and the regional city as shown in the undirected network diagram below. Which vertex or vertices could be the start of an Euler trail? So with an Euler trail, you need either all even or 2 odd vertices. And if we are finding an Euler trail, we want to start at one of the odd vertices. So in this case, we could start at either D or E because they are the 2 odd vertices in this network. Determine an Euler trail. All right, well, there's quite a few, I would say. I'm going to start at 1, so I'm just going to go, D, across to E, down to B, back up to D, down to C, down to A, B, to G, to F. So I'm just going to double check that's correct. So I started at D, went to E, went down to B, I went back up to D, down to C, to A, to B, to G, to F. Whoops, I missed the last one. Back up to E. I need to add that to my answer. Which edge would need to be removed to obtain an Euler circuit? Well, to have an Euler circuit, you need all even vertices. So if we removed that edge between D and E, that means that their degrees would go down to 2, meaning that we would be able to get an Euler circuit because we'd have all even. A courier is to make a daily visit to each site, state whether it is a circuit, trail, cycle, or a path, and whether it should be Euler or Hamiltonian as the preferred delivery route. Justify your choice. So we're not even actually having to calculate or work out any paths or anything here. We just have to determine which is most appropriate. Because we're only needing to visit every site, doesn't matter about every edge, Hamiltonian would be better. And there is nothing in here that says we need to start and finish at the same site, so therefore a Hamiltonian path is the most appropriate. This is a 3-mark question, so you do want to put some detail in your response. Okay. Slam Airlines employ 5 people to complete various tasks required to create an online booking facility. The following bipartite graph shows the tasks that each employee is qualified to perform. Which task must James complete? So looking at James, he can do, I'm just writing J, he can do A, D, and E, but we need to narrow it down to 1. So Lily can only do A, and Haley can only do E. So that means James must do task D. Fill in the table below to show the tasks that each employee must complete. I've already established that Haley has to do A, Lily has to do A, Haley has to do E, which just leaves B and C for Christy and Charlie. Christy is the only employee that can do C, which leaves B for Charlie. All right, the purpose of Beth's visit is to promote 4 new products. Towns A, B, C, and D will sell 1 product each. They have each quoted Beth the cost of marketing each product in their town. Find a possible matching between town and product so that the total cost to Beth is at a minimum. All right, so allocation problem. Let's perform a row reduction. So I'm going to subtract 110 from the first row. That's the smallest. 130 from the second. 130 from the third, and 170 from the fourth. So I'm just going to rewrite it in here. That leaves me with 35, 30, 0, 50, 130, 170, 100, 0, 140, 120, 70, and 0. And finally, 10, 40, 10, and 0. All right, can I cover all the zeros with 4 lines as a minimum? No, I can cover them quite easily with 2. So I'm going to have to perform a column reduction. All right, so if I apply those changes in this column, I now have 25, 120, 130, 0. And in this one, oops, that's not the smallest number. 30 is. All right, so can I do it in minimum 4 lines? Nope, I can do it in 3. So I'm going to have to apply the whole Hungarian algorithm process here. So I'm going to rewrite this down in one of my tables down here. Do blue. All right, so I need to cover them up. There's a few ways I could do it. I'll do it. 1 there, and 1 there. All right, so now my next step is to look at my table, find the smallest uncovered number, and then add that to all covered matrix and all numbers in the matrix. Sorry, and remember that any number that's covered twice, so the intersections, they get added on twice. So my smallest uncovered number here is 70. So if I redraw this matrix, what I'll get is 95, 70, 70. So that'll be 190 because I've added it twice. 70, 70. That'll be 140, adding it twice. 70, 80, oops, 80 and 80. Now we need to subtract the overall smallest number, which again is 70. So I'll do that over here, which leaves me with 25, 0, 0, 120, 50, 70, 30, 0, 0, 0, 20, 60, 0, 10, 10, 70. All right, can I cover it with minimum 4 lines? Yes. Excellent. That's what we want. So the question said, find a possible matching between town and product so that the total cost to Beth is at a minimum. So now I'm going to draw my bipartite graph from this. So we had A, B, C, D. With products, what was it? 1, 2, 3, 4. All right, so A can go products 2 and 3. B, product 4. C, product 3 and 4. And D, product 1. So now using this bipartite graph, we can do the optimal. All right, so D has to be 1, which looking at my original table was 180. A has to do 2 because they're the only one that can do 2, which for A2 is 140 bucks, which leave me with B and C. C must do 3, which means that B must do 4. So C to do 3 was 200 and B to do 4 was 130. So it's quite a process for those marks. If we do the minimum cost, that's just all of them added up together, which we do that, we get 650. All right. The network below shows the path through a national park with the values on the edges representing the number of people that are allowed on the track due to safety concerns. What is the value of the cut shown above? All right, so let's add this up. So that cut, it goes through 30, goes through 45. Yeah, it goes through 31, but we don't count that. It's coming out of the cut, and 16. So a total of 91. Given that the max flow of the network is 70, find the value of X. Again, this is a bit of a trial and error one. You need to work out what your smallest is when you're doing it. So if I did a cut through there, that would be X plus 61. If I did a cut through here, that makes X plus 73. If I did a cut through here, that's X plus 85. So this is the one we're going to be using because that is the minimum cut. Therefore, the value of X is 9. 9 plus 61, making that flow of 70. All right, when building one of the paths, the builders need to complete the number of activities in order to construct the tracks. The immediate predecessor and activity times in days are shown in the following table. All right, so we're going to have to draw up a network diagram here. All right, so let's have a look. A and B are already done. C and D both come off of A. And C and D are both going to be predecessors to F, so it's going to create a bit of an issue. So we're going to have to make a dummy activity. If you see up here that F comes off both C and D, but both of them come off A, that's going to create a multiple edge. So we're going to create a dummy activity up here. All right, we had E down here coming off of B. We had G coming off of E. I'm also going to connect it up to here because H comes off of G and F. And that connects up to J. Give the float time for activity C, and it's also going to ask us to find the critical path and the earliest completion time. So we're going to need to do a full forward and backward scan for this. All right, 0, 5, 6, here will be 8, 9, 15, 17, 22, and for my backwards, 22, 17, 15, 11, 8, 5, 8, and 0. All right, so the float time for activity C is the estimated completion time, which is 8, minus the earliest starting time, which is 5, minus the activity time, which is 2. So that gives a float time of 1. Find the critical path. All right, so this one was A, D, what came after that? A, D, F, H, J. And what is the earliest time which all activities can be completed? That's just the earliest completion time, which is 22. Last question. Determine the shortest path A to E where the distances are in kilometers by using Dijkstra's algorithm in tabular form. All right, so here's a table I prepared earlier. Let's fill it in. All right, so we've got A, B, C, D, and E. A, B, C, D, E. All right. Just do a diagonal of x's, as we often do. All right, now I can fill in my values. All right, so A can get to B and C, B with a value of 18 and C with a value of 21. B can get to just about everything. So we got B to C at 16, B to D at 20, and B to E at 23. Fill in the rows and columns as I do this. C can also get to D for 15. D can get to E for 7. So that's my table. All right, so with Dijkstra's in tabular form, start at the right-hand side with a 0. I'm going to move down the column. The smallest value in that column I can see is 7 at D, so I'm going to move over to D. Moving down the column, the smallest value is 7, but that's just heading back to E. We don't want to do that. So I'm going to go to C next, which gives me a value of 22. All right, so with this one, what we can do is a couple of things. We need to work out now where we want to go. We're not going to go back to D, obviously. We've just come from there. So the next lowest value here I can see is from C is 16 to B, which is 38. It's quite high, which leaves me finishing, at A at a total of 56. But I reckon we might be able to find a shorter way there. So when you're doing these, you can have a look at the diagram to help you as well. So don't forget about that. All right, so I'm going to try this again. All right, so the other option here was to go straight to B from E for a value of 23. Then from there, we can go from B to A for a total of 41. So that's a much better option than that first route that we just did. So that's our answer. 41 is the shortest path from A to E. And you can kind of just look at that on the graph and see that as well, 18 and 23. So whenever you're doing Dijkstra's algorithm in tabular form, double check by looking at the actual network itself. Cool. Thanks, guys.